Good afternoon, everyone. Thank you for joining us. My name is Marissa Waterman, and I'm the Marketing Director here at the Academy. Our Executive Director, Dr. Daniel Other, will serve as the moderator and will introduce our speaker today. During the presentation, you'll be able to submit a question by clicking on the Q&A icon on the bottom of your screen. We will do our best to address each question at the end of the presentation. Before we get started, Dan would like to say a few words. Dan, how are you today?
Many thanks, Marissa. I'm doing great. I really appreciate that introduction to today's webinar. Colleagues and friends of the American Academy of Environmental Engineers and Scientists, today we are pleased to offer you a fantastic award-winning webinar delivered by a board-certified environmental engineer. Webinars like today are what leadership and excellence in environmental engineering and science is all about. And I can't wait to hear more and learn more about the improvements to the South Sioux City Wastewater Treatment Facility. Before we begin, I'd like to take a moment to say thanks. Thanks to you, our members, for your continued financial support of the Academy. It's annual renewal time, and you should be receiving emails with an attached invoice for next year. I'd also like to say thanks to our patrons. As shown on the screen, patrons are firms and utilities who step forward with major financial contributions to support the programs of the Academy. Today's webinar is an example of one of those programs. Today's webinar is free to our members, and that's in large part because of the generosity of our patrons. So thank you, patrons. Thank you for your visionary leadership and for putting your money where your mouth is to support Academy programs. As I mentioned in the introduction, today we're hearing about an award-winning project, specifically the South Sioux City Wastewater Treatment Facility improvements, which received the 2024 Grand Prize in Industrial Waste Practice from the annual Excellence in Environmental Engineering and Science competition. Today's presenter, Dylan Devitt, is a professional engineer. He's board certified by the Academy. And Devin is a triple threat. Not only is he a wastewater process engineer and project manager from HDR, but a great thing about Dylan is he is also serious about his practice. Dylan is a Class 4 wastewater treatment plant operator. I love learning from folks who are living the engineering design aspect, the environmental science aspect, but also reaching out to operations, also reaching out to folks who are actually living these treatment systems on a day-to-day basis. So it is truly an honor to introduce Dylan in this award-winning project. Before we begin, as a reminder, please put your questions in the QA function, and I'll use these as part of a moderated discussion at the end of today's presentation. Dylan, my friend, the stage is yours. We are so excited to hear from you today. Thank you.
Hi, thanks, Dan. Thanks for the introduction. Thanks for everyone for joining this presentation. Just to kind of get started here, like Dan said, I am a professional engineer. I'm currently working in Omaha, Nebraska, currently working in Omaha, Nebraska. Wanted to talk today about this South Sioux City Wastewater Treatment Plant Improvements project that HDR did for the city of South Sioux City about 3 years ago is when we pretty much started this. So to give a little bit of background to what this presentation is going to be about today, there's a lot of topics. I want to talk about the project from kind of when it started, why it started, talk about some of the challenges we had getting this implemented and feasibility study through construction, and a little bit about what we're doing right now on expansion already. So again, starting with our background of the facility, talk about why this project was needed, what we were looking for the outcomes and the objectives, and then kind of dig into some of the details about the design and quite a bit on the challenges we had during the startup. So starting on the background. So South Sioux City, Nebraska is a town located just in the northeast section of Nebraska. It's a suburb of Sioux City metropolitan area. It is just on the south side of the Missouri River, and has a metro population of just south of 200,000 at the moment. Like Dan had mentioned, this project won a grand prize award in the industrial waste category. So keep in mind that this whole system was designed to treat, at the moment, 100% industrial waste flows. So even though it's a city project, it is an industrial treatment system. So about 5 years ago, the conditions of the South Sioux City wastewater treatment facility was there is an industrial district in South Sioux City, and the industrial district houses a handful of industries. The primary industries were ingredient, BPI, a meat processor, Richardson Milling, which does oat processing, and an ingredient facility that did pea protein. There was a for-profit, we refer to it as an REPP facility, which stands for Renewable Energy Production. So they would take all the waste generated from the industries and they would run it through anaerobic treatment and produce biogas, which they ultimately would clean into renewable natural gas source and inject it into the city's grid. That REPP facility ended up having financial troubles and went under. So there was a point in time where all this high strength industrial wastewater was no longer being able to be pre-treated in this renewable energy plant. So all that wastewater and all of South Sioux City's wastewater that they generated in the domestic side would be collected in their sanitary sewer system, and they would pump it across or under the river to the Sioux City, Iowa's wastewater treatment plant. And that ended up causing a lot of strain without the pretreatment facility for the South Sioux City industries. So South Sioux City reached out, they had a problem, and they sent out an RFP. We started talking to them, HDR did, and ultimately we started planning on, well, what can we do to fix this problem? The project needs that for the RFP that we wanted to look at was, of course, the pretreatment facility was out of operation. Because there was no pretreatment from this high industrial strength waste, the city of South Sioux City was implementing capacity restrictions on the South, or the Sioux City, Iowa was putting capacity restrictions on the South Sioux City wastewater coming across the river. Those restrictions limited any future growth of industries in the South Sioux City industrial district. And there was threats of rate increases, and ultimately the city decided they wanted to become self-reliant. So they identified some objectives. They wanted to figure out how to develop the most cost-effective solution for the industries to maintain the ability to grow the industrial area and maintain user rates on the industries as low as they possibly could. They wanted to utilize the existing infrastructure. And because it was an industrial district, a big topic was that if a new industry came in, we needed to be able to expand it fairly easily. And then, of course, we wanted to be energy efficient. We didn't want to be a nuisance to neighbors. We didn't want to generate odors. And if they were ever imposed nutrient limits, we wanted to be able to do that. So we jumped into doing a feasibility study. A little bit of information about the wastewater flow that is being treated at the Sioux City wastewater treatment plant right now. We treat around 2.3 million gallons per day at a max month, around 2. But if you can see down here, for those who have a feel for BOD in the wastewater, BOD, and to give a reference, BOD in typical domestic strength, so stuff that comes out of city sewers, is around 300 milligrams per liter. And BOD is a measure of how much carbon is in the wastewater. Our wastewater was more than 10 times that. So it's very high strength wastewater. So knowing that, we set out and did a feasibility study and looked at a handful of alternatives. We ended up boiling those alternatives down to three main alternatives that we compared more rigorously. We had conventional activated sludge, aerobic granular sludge, and we also compared it against membrane bioreactors. In every alternative we looked at, anaerobic pre-treatment was a must because of the strength of the wastewater. So at the end of the feasibility study, the most cost-effective option monetarily was the aerobic granular sludge. So a couple of things that we were looking at for the flexibility needs for this system was we needed to plan for the ability for the REPP pretreatment facility to come back online. So we needed to see what would happen to the plant if our wastewater strength decreased. We also needed to plan for that never coming back online. So why we ended up with our anaerobic treatment process of lagoons is that gave us the flexibility of treating low strength or lower strength wastewater and higher strength wastewater with the ability for flow equalization, as these industries don't operate 24/7. Many of these industries operate 5 days a week, sometimes 6 days a week. So there's days where no flow comes to the plant from the industries. And those covered anaerobic lagoons were able to still have flow coming out of them to sustain the secondary biological process when no flow was coming in for a period of 2 to 3 days. And then obviously we ended up picking AGS for this facility. A couple of reasons we chose aerobic granular sludge, which did I mention that before? Yeah, aerobic granular sludge, AGS. I'll be saying AGS for most of this presentation. It was a new greenfield plant, so the city had to buy land. And the AGS system has a very small footprint, which was very appealing. Because it has a small footprint and the mechanical aspects of the AGS system, it had lower life cycle costs, it was more energy efficient, and the anaerobic lagoons provided flow and load equalization upstream of it, which really helps out by limiting typical peak flows and maximum instantaneous flow rates that you see in typical domestic systems without equalization. So real quick, I want to kind of take a step back from the project itself and do a little dive into the AGS overview. AGS, or aerobic granular sludge. This is a fairly new wastewater treatment system for the industry. It is classified as an intensified activated sludge. Intensified activated sludge basically means that you're getting more bacteria or biomass in the same volume of a treatment system. And the way the aerobic granular sludge system accomplishes that is it grows aerobic granules. Those aerobic granules have a couple of benefits to them. One, you can just fit more of them in the same volume as opposed to a conventional sludge system. They can grow 2 to 5 millimeters in diameter, so looks like little peas, and they settle very fast. So a big part of wastewater treatment systems is the separation of solids from liquid, and with the aerobic granules, that is much easier.
So you have an outer zone that's aerobic, an inner zone that's
Sorry about that.
anoxic, and then a
I had
center
forgotten
zone
that was
that's
in there.
anaerobic. And so that biological population basically replaces the need for those separate tanks, separate.
So that's a good video with an overview of it. The theory behind the aerobic granules is that they are layered. So in a conventional activated sludge system, we have zones of aerobic systems, anoxic systems, and anaerobic systems. And each one of those systems treats a different type of constituent in the wastewater. With the aerobic granular sludge, those zones are all within each granule. So as you can see in that little animation that was playing, Those spheres have the layers with the anaerobic in the middle, anoxic on the outs or in the subsection, and then the aerobic around the outside. They settle very fast, as you can tell by that picture on the bottom left or right corner of the screen. So how do we form the granules? With the AGS system, we have two primary methods. One is hydraulic selection and one is biological selection. Having a system that selects for PAOs, which happens during anaerobic fill cycles, that helps grow EPS, which is a cellular polymer that helps bind the granules together. And then once we grow them, we keep them in the tank by wasting from the aerobic system the lighter flock. So we grow them, we keep them in the tank by settling them bottom and wasting from further up. And the system works just similar to a sequencing batch reactor or SBR. So they goes in cycles. It fills, it aerates, it settles, and it wastes. So I wanted to jump into a little bit of the design of the plant. So kind of getting back to the storyline of the South Sioux City system. Once we were done with the feasibility study and we selected a treatment technology, we had worked with the state of Nebraska and we had determined effluent limits. This plant discharges into the Missouri River. And because of that, we had fairly or not as stringent effluent requirements as you see in some places. As you can tell, we had 25 milligram per liter BOD effluent target and a 30 milligram per liter suspended solids and some fairly high ammonia targets. Saying that even with high ammonia targets, we had very high ammonia coming into the plant. We went through a design process over the course of about 1.5 years, and we ended up with a site layout that looked like this. Starting in the top right-hand corner or top left-hand corner, we had our anaerobic lagoons. Those lagoons allowed for the first anaerobic pre-treatment of the high-strength wastewater along with the flow equalization for the entire downstream process. That pre-treated wastewater would go into our anaerobic granular sludge system and ultimately out to UV disinfection. We had auxiliary processes to handle biogas generated in the anaerobic lagoon system and the waste activated solids, those generated in the anaerobic granular or aerobic granular sludge system. Show a process flow diagram of the system, a little simplified. Again, this is just forward flow. I won't talk too much about the solids processing side in this presentation, but we had our 2 anaerobic lagoons flowing into our AGS basins and UV disinfection. During our design process, we modeled every single building that was constructed out on the plant. So we were able to detail out everything that we wanted to be shown in a 3D model and rendered those models to be able to show to the city, to contractors, and other stakeholders. Zoom into the AGS reactors in particular. Again, we have 4 AGS reactors. These reactors operate in sequence. So one reactor is always filling at a time. There is no need to stop flow. The reactors fill, and as one is filling, the other 3 reactors are in a either react cycle, a settle cycle, or a wasting cycle. There are effluent weirs inside the tanks, and that is when wastewater comes into the reactors, it pushes the clean treated water out. So jumping over a little bit to talking about some of the some of the struggles we had during bidding and market. If you seen a little bit of that time frame I've talked about, this is right in the middle of our COVID supply chain issues. So this was a huge struggle that we had to overcome. We had an engineer's estimate of constructing this entire facility of around 33 million. And in 2021, we also had Texas storms. We had Texas storms and we had COVID supply chain issues. So we had bids come in very high. Bids opened February of 2021. We had the COVID, the supply chain issues, and all suppliers had very low hold times on their quotes. And we had to go immediately to a value engineering effort in order to make this plant feasible for funding. We were able to remove about $1 million from the project from a VE effort. We were able to acquire some additional SRF loan money, and we were able to talk to a contractor and get them on board with the unknowns that were going to happen in the future. So it was a really, I wouldn't say difficult, but nail biting time on if this was going to happen or not. But thankfully, we were able to figure out a path forward. So once we figured out a path forward, we received bids in February 2021. We gave a notice of award in April, and the construction commenced. We ended up completing construction in June 2023, and we opened the influent valve to the plant July of 2023. So this plant has been in operation since July of last year, and we were able to go through startup and now, and I'll talk about it here in a little bit, but a little bit of an expansion to the plant here in the future. So I got some photos that I wanted to share of this system. So I like this photo because it kind of shows the size comparison. I mean, we have 25 million gallons of anaerobic lagoon capacity. And this photo is right before the covers were put on the lagoon. So they are full of groundwater for leak testing. Flying over to the north side of the plant, you can see the lagoons are here, and size comparison between anaerobic lagoons versus AGS system. The AGS system is much more compact and much smaller, obviously. Just another photo from the other angle. So the AGS system in construction, we have the 4 tanks, and then there is a auxiliary pipe gallery off to the side of the tanks that hold all the piping that sends wastewater to and from each one of the tanks. Inside that pipe gallery, there is quite a bit of piping that goes back and forth. We were able to size it fairly decently to allow for access for maintenance for all valves, equipment, and so on. We were able to put aerobic digesters in to the south of the plant. This aerobic digesters treat our biosolids generated in the AGS plant, and that targets a Class B biosolids. The city ultimately dewaters their treated biosolids, stores them in a storage pad until the months of the year where they're able to land apply them. Dewater with a belt filter press, just a construction photo of it. So construction was complete in around May of 2023, and we started planning to start up the facility. Jumping in a little bit, I want to talk about the startup challenges we had during that time. Like I said, we were able to start the facility up in June 2023. We seeded the lagoons and the AGS seeding from anaerobic system across the river from Sioux City, Iowa. We took some of their waste solids, brought them over and put them in our anaerobic system. We had a neighboring aerobic industrial facility that was able to give us their waste activated solids that we were able to seed the aerobic granular sludge system with. And once we had seeded everything within about a 2-week period, we opened the influent valve and we started pumping raw wastewater into the facility June 12th, 2023. If you remember from that photo I showed a little bit ago, those lagoons were full of groundwater. We had filled them up to leak test the liner. And once we sent that, or we started sending raw wastewater into those, it took a while to turn that over. We get about 2 million gallons a day of raw wastewater, and we had 25 million gallons of groundwater inside that anaerobic system that just had to flush out. Around mid-August, that anaerobic system was able to generate biogas. We were able to burn that biogas in September. Solids were generated in the AGS system. We were able to start pressing those solids in September, and we started seeing our first real granule growth in October. So based on that timeline, first thing we did was we seeded our lagoons. So we had a very large volume of an anaerobic system. We seeded about 20,000 gallons of sludge. So it's not even 1% of the volume of seed. It was almost an inoculant to kickstart the process, as opposed to fully maintain a whole biomass in the system. But we just had trucks come over, filled with that seed sludge, and they just ran for about a week back and forth and seeded the plant. Once we opened up the raw wastewater valve, we started to monitor the operation of the system. The covered anaerobic lagoons run very similar to any other anaerobic process, other than the solids concentration inside them. We monitor alkalinity values. We monitor volatile acids production, pH, BOD, COD removals. One topic that was important during the design and became much more important during startup was the sulfates. And we wanted to monitor the sulfates because the anaerobic system produces biogas that ultimately we were planning to burn in boilers to heat the process. And burning biogas that has hydrogen sulfide in it is detrimental to equipment. So we wanted to monitor the sulfates. And then quaternary ammonia compounds are an inhibitory compound that inhibits biological growth in different types of anaerobic bacteria. So we wanted to monitor that. We did measure some, but it didn't impact the process. And then AGS system was monitored very similar to any other aerobic system, with the caveat of the batch style. So we monitored the CODs, mixed liquors, TKNs, ammonias, and then obviously working with Aqua Aerobics, who was the supplier, on settle time and cycle structure. So during startup, first process that started up was the cows to cover anaerobic lagoons. We had treatment targets of 80% BOD removals, 70% TSS, 10% TKN, 90% fats, oils, and greases. And if you see over on that right column, we pretty much hit all of our targets for each one of our main constituents. This graph shows the performance in terms of the CBOD from the covered anaerobic lagoons. The triangles, or orange triangles, is what we measured coming into the plant, and the The squares is what was coming out of that covered anaerobic lagoon. So right at the beginning, we had flushed out the groundwater in the system, which is what you can see by that curve running upwards. And then there wasn't a biomass really in that system. So over the course of the next 5 or so months, we were able to grow that biomass in the anaerobic system and ultimately make it through a very low BOD removal time and increase it once our biomass generated. And that's kind of a neat graph. I think it shows a little bit of a story on how fast the biomass grew. But in terms of how long it took to pass all that groundwater out of the system, I think this one tells a little bit better. So this is the ammonia readings that we recorded coming out of that anaerobic system. And you can tell that's a fairly nice curved line showing how long it took to almost purge that system from all the groundwater. So it took about 5 months, and past this point, we stay fairly steady on how much ammonia is coming out of the lagoons. So I guess I'll flip right back. So this is kind of the timeline down here of how long it took to purge the system. And that's with the water quality. September 5th, we finally saw that the system had grown enough and was operating efficiently enough that biogas was being generated. So we started seeing biogas filling up the lagoons. So the lagoons are covered anaerobic lagoons, and when the biogas is generated in the lagoon, it just collects in bags or a cover on top. So as you can tell, that looks pretty ballooned up, and that underneath that cover is all biogas. So once we saw the biogas, we started up our biogas handling system. And then I mentioned it a little bit before, but I want to dig into it a little bit more. We realized very quickly that we had a sulfur problem. So our original design for the system had about a 460 continuously generated SCFM biogas flow rate. So we thought we were going to generate 460 SCFM. We thought we were going to have somewhere around 3,000 parts per million by volume of hydrogen sulfide in our biogas. And we had installed a proprietary activated carbon scrubbing vessel that we were planning to take the biogas, send it through the scrubbing vessel that would absorb the hydrogen sulfide. And after that vessel, we were able to use that biogas for beneficial use, or at that point in time, burn it in a waste gas burner. We measured our initial flow rates that we were generating, and we measured how much H2S, and we had up to 2 or 20,000 parts per million per volume. So it was quite a bit more than we had planned. And that higher hydrogen sulfide level made it so our existing scrubber system, the one that we had just installed, had a lifespan of, or it shortened the lifespan by about 5. I mean, we were planning on replacing that media in the vessel every 1.5 years or so, maybe 2 years. And that had dropped it down to 2 to 4 months. And on top of that, the removal efficiency of the unit at that high concentration was questionable. So we planned on using the biogas in boilers to heat the lagoon, and that was no longer an option. So that was a big problem. So we started asking, where's the sulfur coming from? We designed this plant knowing that we had a background sulfur concentration that came from the drinking water supply in the area of around, it was about 220 milligrams per liter of sulfate. And we knew that the industries were protein-based industries, and protein has a sulfur component to it that was going to break down in our anaerobic system and ultimately be reduced to hydrogen sulfide. We started to evaluate where the sulfur was coming from, and we ended up finding out that with the new wastewater treatment facility, we had imposed a little bit more stringent fats, oils, and grease limits coming into our influent, and the industries in response had increased their sulfuric acid usage in their fats, oils, and grease removal systems by quite a bit. So because we had issued a lower influent limit for the pre-treatment agreements to the industries, their response was dose everything with sulfuric acid. So a couple of pieces of info on here on why this was such a problem. As you can tell in that bottom left-hand corner, there's a lab result that we had. That's 20,000. And the OSHA health and safety guidelines are over there on the right, which at 2,000, OSHA lists it as almost nearly instant death if you were to take a full breath of it. So we were not only trying to figure it out on a cost perspective, but it was a huge health and safety issue. So we dug into what we can do to fix this issue. Our first course of action was source control. We talked to the industries, we figured out why they were adding the acid, and we did do a couple of pilot tests with industries trying to reduce their sulfuric acid and see the impacts of their wastewater on that. We did a pseudo feasibility study on different systems to try to figure out which or what the best path forward would be, and ultimately looked at chemical systems and other media systems. We did end up choosing a chemical biogas scrubbing system with the very high concentration. It was the most cost-effective solution in an O&M maintenance thing. We also are still working with the industries to reduce their sulfur injection into the system. So once we had started up the lagoons, we started up the biogas system and troubleshooted our sulfur in the biogas and had a path forward. We then kind of transitioned over to looking at the aerobic granular sludge system. In our aerobic granular sludge system was designed for up to an 8,000 milligram per liter mixed liquor suspended solids concentration. We were running at about half of that. We also had about half of the organic strength coming into it, so it balanced out pretty well. Our operating cycles were right about where we had designed them for, with 1.5 hour fills and 3.5 hour react cycles. And we had very high temperatures. I mean, all the wastewater that came into our secondary treatment system, the AGS, was coming from an anaerobic process that we maintained that temperature at 90 degrees, 90 or 95 degrees. And we also went back and forth a few times on playing with ammonia-based aeration control and dissolved oxygen control. So picture on the right is AGS reactor during one of its fill decant cycles. So this is a interesting graph that I like because it kind of shows the startup challenges we had during starting up the AGS process. So on this graph, we're showing what's coming out of the AGS system in terms of BOD, TSS, and ammonia. And right at the beginning, we had fairly weak strength wastewater coming out of the lagoons. If you remember, we were flushing out the groundwater. And then once that wastewater started to get a higher strength, we had a very poor settling situation that occurred. And that poor settling situation occurred. Everyone scrambled trying to figure out what was going on with it. And we ultimately identified it was a very large filamentous bacteria spike. So for those who know a little bit about the filaments in wastewater, most bacteria settles fairly well. If you get filamentous surge, the filaments look like spaghetti. And I got a picture here in a little bit, I'll show you, but spaghetti doesn't settle very well. So we had filamentous surge that had passed within about a month period. And we thought we were back in the clear. And then we found out we had a mechanical failure where air purge line had started dumping air into the tank while it was settling. We identified that issue, got that fixed. And again, we thought we were in the clear. And then of course, another month and a half later, we had a programming error on our solids handling system. And the solids handling system recycled a lot of solids back to our AGS system, which spiked us up yet again. But since then, we've operated fairly consistently. We don't get the TSS that we thought we would, but it is a very industrial flow, and it is fairly constant. So like I said, I got a slide here showing the filamentous growth. As you can tell, I mean, under a microscope, you should see much more of this, almost none of this. So this is a very poorly settling mixed liquor. But it did pass quickly. This is what it should look like, and this is what it did look like about a couple months later. We have our mixed liquor flock and what we attributed at that time as the start of our granulation process in the AGS system. So I got a couple of photos here showing a little bit of the operation. This is the AGS system during a fill cycle. So during this fill cycle, wastewater is coming in and it is pushing the clean wastewater out the top over those metal effluent weirs. Those weirs are similar to what you'd see in a final clarifier, just inside your tank or inside the AGS tank. We've got a photo here showing the AGS system during the react phase. So as you can tell, that's a lot of solids in the system, and that looks quite different from the settle phase. So this system has worked pretty well at separating all these solids given the industrial waste stream. And then we have another photo here talking about how that mixed liquor has kind of evolved since startup. So this is time since startup, kind of during that startup period, and these are sludge volume indexes. So typical conventional activated sludge usually sits somewhere around maybe 120, 200, and that's what we saw at the beginning. We had our filamentous spike, which didn't help. But once we had passed through everything, we were able to drop those SVIs down quite a bit. And those SVIs really impact our system because when we settle, that settle time impacts the whole cycle structure of the system. So the lower the settle time, the more efficient the AGS system becomes. And then by the end of startup, we were able to measure granule growth. So this one's kind of interesting, and it's a little bit different than what you see in a conventional system. The way Aquarobics measures granule growth is they do a sieve test, and the sieves are very similar to sieves that you would sieve out gravel. You filter the mixed liquor through these sieves, and they have different size holes in the sieves, and that catches the granules, so you can measure if they are 0.22 milliliter, 0.42 or 0.425 milliliter, or anything below the 0.212 milliliter where it's classified as a non-granule. So we had 4 reactors, and the blue is what we call them baby granules, but just the smallest size of a granule that we can measure. And most of the reactors had the majority of their mixed liquor as granules. So another photo here, just kind of showing a snapshot of that AGS system. One of them is an aerate. We have one in fill, and the others are either in an idle or a settle time. So like I said, one of these is filling all the time. So we passed startup. We are continually monitoring the operation of this plant. And we've identified a handful of different issues that have either been fixed with an operational change or identified that need some kind of infrastructure update to it in order to make the plant run more efficiently. And sorry, I think I missed a slide. But in July 2024, the city of South Sioux City signed a contract to expand this plant. So it was kind of an interesting situation, since we had only been about 2 months into startup when we started designing an expansion. And the city wanted to expand this plant for all the domestic wastewater that the city produced, because at this point in time, they were still pumping their domestic across the river to Sioux City, Iowa, and all the industrial waste was being treated here. So in the near future, all their domestic waste will also be treated at this facility. So just kind of showing a little bit more of the trends that we have from startup until closer to today. The covered anaerobic lagoons have been working very nicely. We had gone through our startup period, and we had a fairly nice removal efficiency run for a few months. And then we had a really cold week or two in January, and we lost our caustic system, which caustic system maintained the pH in the lagoon. So we had to fix some equipment before that got back online and operated continuously again. And then we had, if you look down here at the orange squares, we've had a fairly consistent effluent BOD concentration. We are in the expansion planning on upgrading our biogas conditioning system. I mentioned it a little bit earlier that we decided to go to a chemical scrubber system. So the city has had conversations with a third-party entity that actually does renewable natural gas. So the plan in the next year is to install a chemical gas scrubbing system, remove the H2S to very low levels, and then instead of using it at the plant or in the waste gas burner, we'll be sending it to a third-party renewable natural gas system that they will finish the cleaning and bring it to natural gas quality, inject it into the city's grid. And then progress that we've seen so far on our granule growth. If you remember the last slide, we had quite a bit of the 0.212 size granules, but as of April 1st this year, we're seeing even larger. So we are moving, or we are continually moving towards larger and larger granules at the plant. And then again, bringing out that SVI chart to today's dates. So our SVIs had continued to go down. And that's another great indication of how well or how those granules are growing in the system. So finally, as part of this expansion, we are currently, HDR is in the process of designing it. We are adding a domestic headworks to this system, the biogas removal and upgrade, and a whole nother train of AGS and effluent tertiary filtration. So we have our existing aerobic granular sludge system down here, and it is almost a doubling of the capacity of the system. So with that, that is all I have on the South Sioux City story. Open it up to Dan or questions.
Thank you so much, Dylan. Appreciate that. Maybe we'll pull down the slide deck so people will be able to see our smiling faces here. We can chat some. That was a fantastic presentation, my friend. I really appreciate that. That was awesome. That was just really great. Now, we got some questions that came in the chat. I put those together, and maybe I'll go through and kind of like high level, kind of hit the different points, and then we'll come back and kind of pick them off a little bit. So a little bit in the background space. So first of all, we do want to hear you say South Sioux City 5 times really fast.
Yeah.
But no, seriously, there, in the background, right? So one of the early questions is, did that REPP facility already have its own NPDES permit? How did that fit in? And then why didn't the city just simply take over that existing facility and then just burn off the gas if they didn't want to sell it to somebody? So that's one of the early questions, just to understand a little bit about the situation that you inherited. Then in terms of some of the design choices, you had this very high strength wastewater, very strong carbonaceous BOD 5-day. You talked about the anaerobic lagoon pretreatment. We had some questions about why that design decision. I know you talked about flow, you talked about planning, you talked about strength, but if we can unpack that a little bit. And then some folks were wondering, why not consider anaerobic upflow biofilm reactors? So maybe that would be a question that we'll touch in those design choices. Then you went down the path of the granular sludge. Looks like from the photos that there was a lot of footprint. So does that matter? Does that choice consider the fact that you had plenty of footprint to work with? Would an AGS choice be different if footprint was limited? It looks like there was a lot of piping there. So folks were kind of a little bit confused. You talked about a batch system, but then there's all this piping. And so is there some kind of return sludge or waste sludge with all that piping from this system that was described as batch? So maybe we can unpack a little bit more about exactly how an AGS system works. There was a belt filter press. You talked about land application. So then folks were asking like, hey, is there any sanitary in this? Seems like though the expansion is going to have some. So maybe that's a question we'll take with the expansion and kind of think about that. And then in particular, you talked about some seeding. And this is kind of the transition from thinking about the AGS to the covered anaerobic lagoons. Is seeding necessary? Is it just preferred? So we'll unpack that one a little bit, that black gold that you bring in. About the anaerobic lagoons, what was the liner? What was the cover? How were sludge removed, biogas captured? Those bags for biogas that look like big explosive things there. So is there personnel concerns on site for dealing with that? You did get into talking about some of the sulfur and thinking about that upstream fats, oils, grease treatment with sulfuric acid. So is this an example of unintended consequence? You modified one requirement for discharge and you gave yourself a different problem. So if we can speak to some of that unanticipated consequences of design. In your slides on your selections in section 6, where you were talking about bids, you mentioned some good acronyms that may not be common to everybody. You talked about your VE options and what did that mean? You talked about your SRF loan. What does that kind of stuff mean? Lessons learned from being in this place of a consultant, working with a city that had this private entity, private-public partnership, and somebody went bankrupt, and then there's some changes now. Let's add the sanitary. Let's not add the sanitary. So it feels like that you're in a difficult place of trying to meet an awful lot of different requests with your design, all at low cost. So, what are some of the lessons learned? And then, you know, you were talking about the sanitary being brought into the future. You mentioned a little bit about, you know, headworks, domestic headworks to deal with some of the floatables that you'd get, disinfection, tertiary, thinking about some of the discharge, you know, and so aspiring engineers, designers that want to work in this space and deal with these kind of like constant changing operation demands, right? Like this is an upgrade, but this is like the upgrade of let's go this way, let's go this way, let's go this way. So how do people take on the right kind of education and background so they can be responsive to these kind of demands being put on the design engineer? So, you know, you've got experience, you know, with the operator license, but also work in the design. Just feels like this is a really fun, but also very demanding, really great project to work on. So how do people get themselves into the place to be able to take this on? So that's some of the stuff that we'll talk through. We'll go back to the beginning. Of course, now, you know, I said it tongue in cheek. If we can say South Sioux City 5 times fast, that would be great. But why not just have the city take over this RPP biogas facility that was there and just burn off the gas if they didn't want it? Like, why go down this path? What was, you might have inherited this, but how did you end up in the place of doing a wastewater facility when there was already something there designed to deal with these high strength wastes?
Mhm. So the REPP facility that was in South Sioux City, it was a private owned entity. It was a for-profit entity, and the design of it didn't account very well for the fact that the industries didn't operate 24/7. So they had lots of problems. And during the last few years of their operation, they actually went into a substantial amount of debt with the city. And to this day, they're still in litigation. So it was a kind of a time-based decision. I mean, either you try to figure out how to own it at some point, or you got to make a decision now. And they made a decision.
Okay. Okay. So that's the thing you inherited. So they had this prior relationship, public-private partnership, and this kind of thing going on. And basically there was a decision made by your customer, the city, and they said, here's the direction we're going to go. And so now you inherited that. So yeah, so that wasn't an option in there. So now you had design choices. You had this high strength, high carbonaceous BOD. You were talking that some of the reason you wanted to do an anaerobic lagoon pretreatment was because of the strength. The flow's only 5 or 6 days a week. There might be bringing that REPP back online, maybe not. So, you know, can you help us understand what were the thought process that went into the anaerobic lagoon thought? Why not an anaerobic upflow biofilm reactor? If you can speak to those a little bit.
Yeah. And I like that question because I had the same one at the beginning of design. I mean, lagoons seem like they're such an old tech, right? And they are. But at the same time, if you have the land and you need the equalization for 2 to 3 days, when you have a flow rate that's around 2 million gallons a day, that's a lot of flow equalization. So it just came out to costs. I mean, they are simple. I mean, it's a hole in the ground with a cover on it, right? So it was a cost because the upflow would be more efficient, but we would have had to also include equalization on it.
So you didn't, yeah. So basically, bottom line was the cost of land made it simple to put the hole in the ground. That was all you needed. So okay, makes sense. And so it wasn't. So when you looked at it, it was just overwhelmingly the cost for the land made it just so worth it. So then when we get into the AGS system, right? So it's funny, right? Because on one hand, you're using kind of like the classic hole in the ground lagoon, and then AGS system is kind of like, you know, the high end bells and whistles on the other, right? So it's like you've got this really new thing that not many people have, and then there's this hole in the ground thing that people have. So let's explain the AGS system to folks a little bit more, if you would, right? So, you know, you talked about it being a batch, you talked about it as operation. We saw some pictures, had lots of pipes and stuff though, right? So I think folks are a little bit confused. Is it a continuous? Is it a batch? Is there return sludge? Is there waste sludge? Can you talk us through how AGS works a little bit?
Sure. So if you focus in on just one reactor in one of those AGS systems, the cycle structure of an AGS is it'll start filling, and when it fills, it is right after the system is done treating. So it's full of what you would consider treated water and biosolids. So when that AGS system fills, it fills from the bottom, and as it fills, it pushes the clean water out the top.
Okay.
And then when it's done filling, if you remember, there were weirs at the top. That water level's right at the top of that weir, and before that system can turn the air on, it has to drop that water elevation down about 12 inches, 8 inches, 12 inches. So we call that a water level correct cycle. So when it's done filling, it does a water level correct, it takes the water down, and that water then gets recycled back to the head of the plant.
Okay.
It turns the air on, and then when it's done treating, it settles, turns the air off, lets the sludge settle, and then it does a waste cycle. So it takes the waste activated sludge from around the 2/3 to middle elevation in that water column and sends that out. So all that piping that you see inside the pipe gallery, there is 3 main pipes. There's a feed pipe, a water level correct pipe, and then a waste activated sludge pipe.
Okay.
And
it's
all of those
it's
go out.
physically a batch reactor though, right? So
It's physically a batch reactor. Yep.
okay, fantastic, fantastic. So batch reactor, you're almost using that granular bed as a kind of a filter for that upflow, right? So yeah, okay, okay, makes sense, makes sense. So it's kind of an upflow filter for the granular bed so that the water pushes up, but just hydraulically, you're not filling it so fast that you disturb that bed. So you bring some water in gently and it just pushes hydraulically the clean water out the top of the tank. You bring it down a little bit. So the only recycle line is that little bit of hydraulic you're giving yourself at the end, and you're just recycling that back. So you're not recycling sludge, you're recycling back some clean water in a sense.
Yep, in a sense. Yep.
Okay.
That's exactly
okay.
what it does.
That helps. I think that'll help people kind of get their mind around that system. So you had a belt filter press, you talked about storage before land application, right? Is there any sanitary in that? I mean, obviously those industries have got employees. So where did that sanitary, like you were basically really focused in on what was there with the industrial high strength waste, but does that have some mixed sanitary coming from the employees at the facilities, or did your land application look exclusively at regulations that were like, hey, this is just industrial, there's no sanitary in there to deal with? Can you speak to that? And it looks like in the future you're going to have a different answer to this question, but but currently, any sanitary in there, or could you just basically look at it exclusively as an industrial treatment system?
So the industrial district over in South Sioux is fairly old. They have some separated sewers. They have some smaller industries that are not separated. The plan was always to bring domestic in. So we chose not to go down the path of making sure we had no sanitary waste at all. I mean, there could be a little bit, and we just said, we're planning for bringing domestic anyway. We're going to treat it like it's domestic.
Got it. Oh, got it. So belt filter press and storage before land application, you were already thinking biosolids as one that would have some sanitary domestic in there as well, right? Yep. So, you did talk about land wasn't a constraint. The photos, plenty of space out there that explained the anaerobic lagoons, but AGS, is footprint an issue there, or is there a footprint issue between conventional activated sludge and AGS? Any better in terms of efficiency of land footprint there?
AGS is more compact, right? So typical activated sludge system runs around 3,000, 4,000 milligrams per liter. AGS runs around 8,000 to 10,000. And it's a 1-to-1 ratio. If you double your mixed liquor, you cut in half the volume you need.
Okay, fantastic. Makes sense. Now, I saw your smile on your face when I mentioned that we were going to get to the seating, right? So this is our transition between the AGS and the anaerobic lagoons. So seating. Needed, not needed, preferred, not preferred, where from, anywhere? Can you speak to that a little bit? Because again, you mentioned like, hey, it's kind of a really small inocula, less than 1%. So there's got to be some cost. Yeah. Does it do anything?
I don't know. I did a fairly good survey with people in my company and outside my company asking that same question, right? And what I found was it was about a 50-50 split. Some people said hit it, hit it high strength and keep it hot and it'll work. And some people said I'd recommend seeding because they thought it would cut your startup time in half or more. I have one data point, which is this lagoon startup. So I'd love to try it again without, but
that isn't going to happen for you, I
Yeah.
don't think. But yeah, so you went with it because, but you didn't find something in your engineering where overwhelmingly you said this is a must. So it felt like it was the right thing to do, and it felt like it was at the right cost to be able to get it done and the right flexibility to get it done. But you didn't have overwhelming, it's got to be done.
Sioux City, Iowa said you can have it for free. And we said, if you're going to give it to us, we'll take it.
Fantastic, fantastic. So now if we talk about this anaerobic lagoon, composition of liner and cover, how did you get sludge out, or will you get sludge out? How do you deal with the biogas you're capturing? If you can speak to those a little bit.
Yeah, it's HDPE liners and covers. So it's basically a really big HDPE balloon, right? And water comes in. We do have piping that runs to the bottom of the lagoon, and there are pipes around the perimeter of the lagoons that you can bring vacuum trucks to suck the sludge out the bottom. We have not had to do that yet. We expect it'll be about a once every 4 to 5 year operation. But
of right now, you haven't had to pump it out yet. So
Right.
So these big balloons of explosive, flammable biogas sitting there, right? So personnel concerns on site, safety issues associated. I mean, obviously, you're not, you're intending to be able to use it if it didn't have too much sulfur, to be able to make some heat, to be able to operate the system. So we got that part. But any things that you had to think about in terms of personnel safety for doing these covered anaerobic lagoons out where you were with biogas capture?
Yeah. So we follow, and I'm forgetting the standard right now for design. Shoot.
You knew I was going to ask something that was going to get you to the
Yeah. I'm
technical
forgetting what the actual standard's called. I mean, everything that handles biogas in the facility is rated as a class 1, division 1 explosive piece of equipment. Rooms need to have enough air exchanges for those classifications, and that's for the methane explosion potential. And then in terms of the hydrogen sulfide, the operators do wear monitors that will go off if it is measuring over a 2 ppm limit.
Okay, so that's all. So they're all there to be protected from that. Because you did show the OSHA standards, particularly when you got into the sulfur space, which is interesting, right? So there you get the rule of unanticipated consequences. You thought you'd make your life a little easier by adjusting how much fats, oils, and greases that your dischargers could do, but then they got rid of their fats, oils, and greases with the classic fog removal of sulfuric acid. So then you ended up with more sulfuric acid. So was that just Peter Paul not talking to each other kind of thing, or is that like a, hey, lesson learned, I'll never make that mistake again? Or how did that unfold? And realize you're talking to a sympathetic audience of other folks dealing with designing. So did you just wake up one day and say, shoot, I guess we did that left turn? So how did that happen?
Yeah, I mean, it's a huge lesson learned. If I had to go back, I'd press the industries 5 times as hard as I did in the beginning on figuring out what they have. One of the main industries in question during that point in time was doing a pilot test for hydrochloric acid.
Okay.
And when we asked them what they had, they told us, but then that hydrochloric acid test ended up being suboptimal and they switched back to sulfuric. And lo and behold, now we have a whole bunch of sulfur.
Got it. So be careful of how your surveys go. So when you would say you would press further, just try to understand it better. So what would have been, kind of lessons learned, right? So other folks find themselves in this spot. So did you just kind of like send a survey of what's going on, or meet with the people further? Like what would be other engineers and scientists associated with the academy finding themselves in this kind of place, doing this kind of stakeholder engagement, trying to figure out what they're doing with their design? do you have some practical, like, hey, folks, make sure you always do a couple, what would be some practical advice you might leave people with from this kind of lesson learned for yourself?
Uh, I if I were to go back and talk to the industries again, I would like to have identified the sulfur being a more critical issue. So especially in this situation, we worked with the state to set their pretreatment permits.
Okay.
And we did not include sulfur as an oversight in their permit. We wanted them to record it, but we didn't set a limit. And it's something that we should have set as a limit. We just didn't imagine someone would use that much sulfuric acid. I mean, it's
You didn't know how much fat there was going to be in their waste. So, okay.
so
No, it's
don't
fascinating.
don't assume, come up with realistic limits is the advice.
Yeah. So you had identified, from a design perspective, you had identified the importance of sulfur, but then when you got into the working in the pretreatment regulatory space, it didn't translate as important an issue maybe as it could have been, because you just was like, hey, we're great. There's never going to be that much sulfur. Turns out, whoops, there can be that much sulfur.
Yes, there can.
Oh, fascinating. So along those lines, a little bit of a transition, right? In terms of going from the engineering into other spaces. In that case, with the sulfur, it's kind of in the regulatory space, but your section 6 was all on the bidding and the financing and how this worked. And you had some terms in there that maybe not everybody's familiar with, right? So you talked about your VE options, you talked about your SRF loan. Can you unpack a little bit more of that stuff so that folks can follow what that is?
Yeah. So VE is value engineering. For us anyway, it was engineering effort that we did once bids came in. So a typical project, or design bid build anyway, you give the contract documents to the city, they advertise it, a contractor bids on it. And we were 7 million low on our engineering estimate compared. So value engineering is we take things out of the project, or we optimize pieces of the project. Or so I guess, yeah, I mean, it's trying to make the project cheaper by doing a engineering review of the design. So that was our value engineering. And then our SRF is a state revolving fund. It's a financing agent, or a financing avenue that municipalities can go through to get loans from the state to projects, municipal projects.
Fantastic. Well, just it helps folks kind of understand those, because it's kind of like there's the details of the granular sludge, the details of the anaerobic, and the academy's got folks that are coming at this from all different angles. So it's good to hear some of those kind of details and how you do financing of wastewater to be able to help make that translate across. So, lessons learned in terms of public-private partnership, constant changing. This is kind of in this funding space. So now you've got new demands being placed on you. Hey, we want all of the sanitary to also go here as well. So, what's that like from an engineering, thinking about over the horizon and what you're trying to design for? How do you incorporate in this large space of options that your client might ask you for when you're trying to also come up with, a least cost? How do you balance that future forward kind of vision with that? Here's what I can get done for you today for the least cost. How did you come about wrestling with that?
Yeah, that one's difficult, right? I mean, the city was able to acquire so much funding, and that was a huge issue, or that was a huge driving factor on why we are now doing the expansion, because cash flow. They weren't able to get the funding to do the entire thing in one go. So we got the industries involved. Once the industries were connected, they were able to pay their fees for their sewer bills, and that is avenue that we were able to leverage to get the funding for the domestic.
Fantastic. Makes sense. We got some questions in there. Folks were asking about, the headworks that you're talking about once you're adding domestic, the tertiary once you're adding domestic. There's some people saying, how about PFAS? How about microplastics, right? So as soon as you start getting into this, okay, well, now we've got, domestic stuff. Is that changing the way you're looking at this facility? Because you've basically got an industrial facility that you've optimized really well around that. And now suddenly you're going to have all this sanitary domestic flow going through it. Is that going to, keep you up at night trying to have it meet all these, what we think are the coming regulations associated with PFAS and things that might appear with microplastics? How are you balancing those in your future upgrades and plans?
That one's hard. I mean, microplastics, I can honestly say we haven't considered too much on microplastics. The PFAS is an ongoing issue. We are right now land applying. If we can't land apply, we will have to figure out how to get it to a landfill or I mean, it's kind of the issue with PFAS. What do people do if they can't get rid of it, right? So it's something that I say that we have our eye on, and we're trying to understand how that's evolving, but we are still trying to move forward with doing things the best way we can for the city and the consumers. Yeah.
Sure. Totally makes sense. Totally makes sense. That tertiary treatment that you had on there, is that because NPDS for human contact on the back end? Is that something in there with some disinfection, or what was that about?
It is a effort to reduce sulfur, which sounds weird. I mentioned a little bit, we did pilot tests with the industries to reduce their sulfur. And when they reduced their sulfur, they ended up discharging a lot more colloidal solids. So solids that stayed neutrally buoyant in suspension, and they were not removed by gravity settling.
Okay.
That since we disinfected with UV, it killed our ultraviolet transmittance in the water. So the UV
They're shadowing everywhere. Yeah.
So we are putting the filters on and to give the flexibility for the industries to reduce their sulfur, which is a main driving factor of it.
Okay. So you still have
those colloidals. Yep.
Okay. It's to get those out so then that your UV will work for your tertiary. Okay. Makes sense. Kind of, I've been able to pull together a bunch of the questions that have come to folks, but now we're in this space where it's kind of speaking to the folks that are either students or emerging professionals, right? You're a board certified environmental engineer. You've made it, right? You know what you're doing. How do aspiring design engineers, you've got this background with an operator license as well. You've got your PE, you're board certified. What advice would you give for people to bridging that idea of practice, that idea of operations, that book learning, the things that they get kind of in the classroom? How do you bring all that together to be an expert like you clearly are with this project?
Best piece of advice I have in the wastewater world anyway is get in the field, right? I mean, if you have the opportunity to get out there, whether it's a construction project, whether it's an initial survey of an existing wastewater treatment facility, I mean, just being out there and seeing it in real life versus on paper or on a 3D model, and being able to talk to the operators. Operators are great people. I mean, they're really fun people too. So you can have a lot of fun with them. So I do think that's, I mean, yes, the education's a big part of it, but being there and hearing from them and getting their opinions, that's invaluable.
Fantastic. Anything else you'd like to leave the audience with, Dylan?
Appreciate you taking the time to listen to this story. I'm sure if you got any additional questions, you could reach out to Marissa or Dan and they could share my email and be in touch. Thank you.
Dylan, thank you so much. Congratulations again on an award-winning project, and thank you for a fantastic presentation today. We really appreciate you being here with this webinar. Marissa, we'll turn it over to you.
Okay, thanks, Dan, and thanks everyone for all your questions. Especially thank you to Dylan for sharing your knowledge with us today. We do have several webinars planned in the near future, so you can go to aaees.org/events to reserve your spot. Just a reminder, if you're not yet a member and you're considering joining the Academy, please email me to discuss our membership options. Our PDH certificates for this event will be sent out this week to board certified individuals. That's all for now. We enjoyed being with you all today. Thank you so much and have a great day. Bye-bye.